and she works at the University of York, and she's going to speak to us about smooth entropy in axiomatic thermodynamics.
Okay, so thanks to the organizers for the organizing, but also for allowing me to present my talk here. And I will be speaking about an axiomatic framework for thermodynamics that I've been working on for a while, together with Lea Kramer-Gabriel, Philipp Feist, and with Renate Renner. And I want to first kind of motivate why we've become interested in looking at such a framework. So the idea is that we wanted to look at different approaches to thermodynamics. So I would say roughly one could say that there are two types of such approaches. So one would be a phenomenological approach, where we would just describe systems in terms of macroscopic degrees of freedom. So like we do in classical thermodynamics, we could speak about the volume of a gas, for instance. But then there are also other approaches where we refer to these properties, and most axiomatic frameworks kind of belong into this type, I would say. But then we can also take a different approach, a statistical approach, where in order to describe macroscopic systems, we actually refer to the individual constituents. So for instance, to the movement of individual particles. And here, we'd also count the information theoretic approaches like quantum resource theories or this treatment of Maxwell's demon that we've heard about. Okay, and so of course these approaches are all related because they all lead to the laws of thermodynamics as we know them. But what may bother you, or what did bother us about this, is that to some extent, even though we all know there is this relation, it's really hard to kind of spell out in an explicit way. So it's really hard to formalize this, mainly because these approaches all refer to different quantities that may not even be defined within the other approaches. And so it's hard to kind of find an explicit connection. And so for this, we have tried to come up with such a framework where you can kind of take both approaches within one framework. And we also want this to apply to different regimes, so not stay with the large systems like in classical thermodynamics, but for instance also move to microscopic systems where, for instance, things like errors play an important role. So we want to come up with a framework that can do this. And I will hope to convince you that we have done that. But first, I want to say a little bit about these axiomatic approaches, because we base our work on other such approaches, and I think they're maybe not as well known. And so I want to say a little bit. So as far as I'm aware, the first to come up with an axiomatic framework for thermodynamics was Kara-Theodori around the 1900s, and he looked at spaces and whether he can find certain adiabatic processes. So his framework has a postulate that says that in every neighborhood of any state, there should be at least one state that can't be accessed from it with a reversible adiabatic process. And this has kind of been carried on through the literature. This idea of looking at the state space and processes has been taken up, for instance, currently in resource theories a lot. And one particular framework we have been working at is by Lieb and Ingvason. And I want to kind of give you a flavor of what this is like. So I've just picked out some aspects that we will need. Of course, this is by no means a complete account, and I would just refer to this paper for anyone who's interested. And so what they have is also a state space, and this would be the space of all equilibrium states of a system. So you can think, for instance, of a box with an ideal gas. Like here, it could be described by the internal energy and the volume. And then they consider adiabatic processes on these systems. So what this means is an interaction with some environment. Here I've represented this by some device that has a weight attached to it. And in such an adiabatic process, the only state change on this environment that is allowed is a relative change in the position of the weight. So you can essentially do work on your system or extract work. And these processes then induce an order relation on this state space. So if I can find a process from X to Y, I would say X precedes Y in this ordering of states. If we think in a resource theoretic way, you'd say X is more valuable than Y because you can use it for more things. Okay, and then we need other operations. So for instance, you need to have a way to say, what can you do if you have two systems at your disposal? So you can do, for instance, mix the systems or do operations on both of them. Another operation, which is kind of what makes it thermodynamic, is that there's a scaling operation. So there's assumed to be a continuous parameter with which you can scale your system. And intuitively here with the gas, we think we just scale the amount of substance. So here the extensive parameters also scale. Okay, and then there are a few axioms that I don't want to go into that should hold for this. But what I want to show you is what then the statement of a second law would look like in terms of these operations and in this language. And so very informally, this is this. So for an entropy function, what you're used to is that it's additive under composition of systems, it should be extensive in the scaling factor, and it should only increase under adiabatic operations. And this function looks like this. So there is an essentially unique function up to some scale. I want to quickly say what this means. So if you think about a very simple example of 5 states here, I have here kind of made up that there's an adiabatic process from this to this, and each arrow kind of would indicate an adiabatic process. And then I can pick 2 reference states in my state space. So here I have this one, which I call x0, and one that I call x1. And then the question that specifies the entropy is essentially how much resource do I need to produce my state. So if you think about it, from x0 you could always get your state x in an adiabatic process, just doing these 2. But now the question is, if I only want part of my system to be in that state, and mix this with a less resourceful state, which is called x1, what is the optimal ratio I can do this at? And this is what gives the entropy here. Okay, so this is how one can understand this. And then, of course, there is much more in the framework, so there are further axioms on the state space as well. And one can not just get an entropy, but also, for instance, for some types of systems, one can define a temperature and then talk about isothermal processes and about Carnot efficiency and all of that. But it's not what the talk is concerned with. So there is one more remark I want to make, and you've probably already picked up on that. So what this establishes is kind of just the structure of a resource theory, a particular one in this sense. And what one can do with this, and is something we've done in a previous work, one can also connect this to quantum resource theories. So these work also fit into this framework. Now, there were several restrictions with that. So one restriction that there is that systems have to have a certain size for this to make sense. And the other thing is that maybe this structure doesn't make sense for small systems because you have errors that play a role. And you may then want a different framework that can account for this. And so this is what I want to present. I want to also convince you that maybe errors don't only make sense for small systems, but also otherwise. So, because if you think we have here, as before, we want to have adiabatic processes, all I can now say is from this state to this, I can't find one, but the other way I could go. And the same is true if I have this other state where the energy is just slightly higher than here. But now if I'm in a situation where I actually have to find the energy maybe of my output state, maybe the accuracy to which I can measure is not as exact as I would hope, and I can maybe not even distinguish the two. And so in that case, I would want to have a means to say up to which precision do I have to go in order to be able to do the process. So if I make a very simple example where I fix the volume, for instance, I can say, well, now in this output, I accept an error tolerance in my energy. And now I can say what error tolerance I would need in order to be able to do the process. Now maybe this example seems a bit contrived, but you can think of, for instance, randomness extraction, where we actually care for things like that. So there, if you want to extract randomness, maybe if we say we allow for an error, instead of having the uniformly random bits, then we can extract much more randomness from the same data than if we wouldn't do this. And so in that sense, it can be also resource efficient to actually consider errors, and it's not just, this is actually useful. Okay, so now I want to say what the properties are with NSUme. So we keep kind of the state space, where we don't talk about equilibrium states, but just the state space and the composition operation. And now instead of a pre-order relation, we have many of these error-tolerant order relations for which we have certain properties we assume. And I want to argue that these are rather natural. So one thing we want to assume is that we can always do nothing to the system. So this can be for any error tolerance, we can just not do anything. And this should be allowed. Then the second thing says that if we have a certain error tolerance at which we can do a transformation, and now I say, well, actually, I want to have a bigger error tolerance, then my process that I could do before should still be allowed, because I even allow for more errors. This property is kind of replacing the transitivity that we usually have in the resource theories, because you can just concatenate processes. But if you think in a probabilistic manner, then if you have an error in a process and in another one, these errors may add up if you want to do both processes. And so this is what this says. And then the last one says essentially that if you have a process and you add a system on which you actually do nothing, and that shouldn't affect your, then that doesn't have to affect your process. So you can still do the transformation and just leave the additional system alone. Okay, and this is what we consider in general. But now we have the issue that what we can't do is kind of quantify the resourcefulness of our states. Because before we have seen there was this continuous parameter from the scaling, and now there is kind of no parameter that can tell us anything. And what we need now is what is called a meter system. This is just a family of states that are assigned a value. So here the value would be lambda, and this would just be n states with a certain value. Yes. Okay. And the idea is then to have this meter system interact with your system, and then you can tell what resource did I use on the meter, and this will tell you something about the process that happens on your system. And if you do this with a reference, this will tell you kind of the value of the state you derived at. But this should become clearer. So an example of a meter in the case of the thermometer from before would just be an example where the value of a state is the first component, so it's the energy. And for these meter systems, we need a few more properties, because first of all, they should kind of measure our systems, so they shouldn't act as catalysts. So the properties we have is here what I just said. So a meter shouldn't be a catalyst, because if I want to have a process on my meter that tells me kind of what happened on my system, and allow for a catalyst that in the worst case allows for any process, then this meter is completely useless. And so that's why we can't allow catalysts here. And then the other two properties here are mainly here for the way we want to label the meter, because we want our properties, we want them to tell kind of, so, how can I say? So we want them, our properties about the system to kind of have nice properties. So we don't want to randomly label these states, but we want to monotonically label them with the order relation. So a more resourceful state would have a lower lambda in this case. The other thing is that if we can convert certain meter states, so we can put two together and get another one, we think this should have the same value because they can be interconverted. And then the last is what we call an error resource trade-off. And what this says is that errors can allow us to do more transformations. So if there is a process we can't do and we add an error, maybe it can now be possible. And this is characterized by a function that should be 0 for a 0 error, because there nothing should be possible. And otherwise it should be non-decreasing in epsilon. So in the example here, or from before, you could have just that the function is equal to epsilon. It was just a tolerance that we allowed in the U. But for instance, if you look at some probabilistic thing where the errors are between 0 and 1, and for error 1 you'd want to do anything, you'd want to have something that is, for instance, logarithmic in 1 minus epsilon to get this. So this depends on what errors actually mean. Okay, so this is kind of what the framework looks like. So we have these properties for states and these additional properties for the meter. And we can now use the meter to, yeah, sorry. Yeah, so there is no value assignment to, it's not quite clear. I mean, they're ordered in some sense, but you want to maybe say, what is the value of my state with respect to a certain reference? So you might want to assign numbers, so to say. Okay, so the idea is that if you start with a reference state on your system, and you want to generate a certain state, you can do this by at the same time doing a transformation on the meter. So it can be that you can anyway go from the reference to the state, then this transformation can allow you to extract resource, or it can be that this is not possible, then you would invest resource in this process. And you can do this for any epsilon. And so we define these two quantities that should look similar to the entropy from before. So here we kind of make the state, and here we deconstruct it again with the meter, and this assigns a certain value. Okay, so this is the idea. And this reference state is an arbitrary state on the meter, so it doesn't, on the system, it doesn't really matter what we choose. And now what we can do in terms of these is we can find a second law-like statement where we have a sufficient condition for a state transformation here, and we also have necessary conditions here. So this is kind of the analog to the statement we've seen before, just in this new framework. Okay, and so this is the idea, and that now I want to tell you also how we apply this. So first of all, we can apply this to the statistical approach. So far I've been just talking about boxes of gases, but we can think about states that are described by density operators. And then we have to have an explicit model of what an adiabatic process is now, because we want to know how this affects my state. And this is the way we define this. So we use this model here by Johan Åberg, where essentially the weight provides coherence as a resource. So we use this weight, and what this allows us to do is essentially to do any unitary. So we allow to use some environment, and then do a unitary operation, and we don't want to see any change if we just look at the environment at the end of the process, whereas the weight change is here not explicit because this is in the unitary here, so the state of the weight change. So this is how we define adiabatic processes. Then there is a composition operation, which is just a tensor product here. And we look at errors, and this is quantified by means of the trace distance, because this makes sense because it's related to this distinguishability that we may be experimentally interested in. Yeah. Or sharp means that all the non-zero eigenvalues are equal. And so it's there because we don't want this there can be an environment kind of involved, and we can build up correlations with it, but we don't want to it to act as a catalyst. So it shouldn't, the process shouldn't depend on the shape of the environment. Okay. Okay, so this is how we would set up this resource theory in the statistical approach. And what we then find, if we use a meter system, this, for instance, a battery system, so meaning our meter system is n qubits, where log d is the dimension of the Hilbert space of the system we've seen. D is the dimension of the Hilbert space of the system from before. So we use n qubits. That can be either pure or mixed, so they are in states like that. This would be our meter, so a battery system in a way. What we then find is that these S minus and S plus correspond to certain min and max entropies. So I didn't add the definitions here because I don't think they're very instructive in this context. But if you want to think of it maybe in a picture, so if you draw the step function, the spectrum of your state rho as a step function, so these are just the eigenvalues in decreasing order. This H min here is just the log of the maximal eigenvalue of this subnormalized state if you cut off this epsilon here. And for the S plus, you would just cut off from the other side, essentially. And then here, the log of the rank will be what this quantity will give you roughly. And so this makes sense because actually what I forgot to say is that our operations are related to majorization. So actually, our adiabatic processes are there if the first state majorizes the second, and then it makes kind of sense because you want to produce your state, but you're happy to be there up to epsilon. So this state is kind of the closest you can get, where you need to normalize, but that's not an issue. And that's also why these references are here, because this is closely related to this work on approximate majorization that has been published recently. Okay, and now in terms of these S minus and S plus, we had these necessary conditions and these sufficient conditions. So this is the necessary condition would now look like this. And so we can use these to characterize whether we find processes or not. Now the second application that I will just mention very briefly is that we can get from our error-tolerant axioms back the structure of the resource theory that you'd have if you weren't to consider errors. And this means that we have to define a macroscopic state space, which we do by letting states being functions of some real parameter. So for each real number, we have a state on a different space, and where n can be imagined intuitively as increasing the substance. So one example could be here a gas, where each state is just scaled by n. So it's essentially the same state, but on a larger system. Okay, so, and then for this, we can introduce a macroscopic order relation. So it's a macroscopic state X can be transformed into a macroscopic state Y if for any error tolerance, we can find a large enough, for large enough system size, we can do the transformation. This is the idea. And what then comes out is a second law-like statement for equilibrium states like the one that we've seen before. So this macroscopic entropy function completely characterizes whether there are transformations or not. And there is more, so we can also recover the axiomatic structure of the other axiomatic framework, which I haven't really introduced here. And if we look at, in the statistical approach, at certain classes of density operators in this, we can, for instance, for IID states, get back the von Neumann entropy. Yes. So I think with this I conclude. So I have presented our framework for error-tolerant processes. And what is nice about it is that we don't need any macroscopic reference or any scaling operation. I've also found an operational meaning for these H-min and H-H quantities related to what resources we need to make a state in these, with these transformations. We have also seen that from these kind of statistically inspired axioms, we can recover the phenomenological laws as we know them. Yes, and there are many open questions. So I just want to quickly mention two of them. So one thing is, this framework is, of course, not restricted to adiabatic processes, but you can also, for instance, look at thermal operations. So they will fit all the axioms, and you could consider that where you think about a heat bath, essentially. And so the question is if we can get any insights from this that are interesting, which we don't know yet, and whether there are further applications of the framework as well, maybe beyond thermodynamics. Another thing I'm particularly interested in is to see what processes with quantum side information would look like. So for instance, whether one could kind of see conditional entropies also in this context. And my time is up and I would like to conclude. And thank you for your attention.